All right, so um, we're going to start with chapter 13 material, which deals with ethers and epoxides. So these are two functional groups that are similar. Ethers are any carbon-oxygen species where both bonds to oxygen are carbon groups. So that's the general structure of an ether. And then an epoxide is a subset of ethers that are constrained within a three-membered ring, which we've seen before. So this is an epoxide. Okay, and so we're going to talk a little bit about reactions of ethers and epoxides, and then also some strategies for their synthesis. The nice thing about ethers is that they're generally unreactive. And actually, they typically are used for solvents because of that. So they're often so unreactive that we can use them to dissolve compounds to carry out other reactions. Epoxides, however, are highly reactive, again, because of that three-membered ring. So a lot of ring strain there, and so they're quite easy to ring open in the presence of nucleophiles. And so epoxides are very synthetically useful. Ethers are typically not very useful. What we end up doing with those, again, is just using them as a solvent. You do know a few ways to synthesize ethers. And in fact, all of the ways that you've learned come right out of Organic 1. So the first route that you have learned is the oxymercuration of alkenes. So remember, we used that oxymercuration to make alcohols when we used water, but I can, instead of using water, I can go ahead and use an alcohol as a nucleophile. That will allow me to make an ether using the oxymercuration. So much of it is the same. We use mercury acetate, but here's the difference. We're going to use methanol as the nucleophile instead of water. And then again, we have to finish this up with sodium borohydride to remove the mercury. And what this gives us is that Markovnikov addition of hydrogen. And since we have methanol as the nucleophile, methoxide adds at the more substituted carbon. So this works with small alcohols. So practically speaking, that's going to be methanol, and that's going to be ethanol. But this is a nice way that we can use to make ethers directly from carbon-carbon double bonds. So we can use another example here with 1-methylcyclohexene. If I add mercury acetate, ethanol this time, follow that up with sodium borohydride. Same idea, the hydrogen's going to add to the less substituted carbon, and then that alcohol will generate the ether at the more substituted carbon. So that's one route that you guys learned in Organic 1 to make ethers. The second sort of more versatile route is by substitution. This is a reaction known as the Williamson ether synthesis. And this is essentially an SN2 substitution to make ethers. So here's what that would look like. Take, for instance, an alcohol, treat that with a base, such as sodium hydride. That will give me a strong nucleophile at that oxygen, so I would get the sodium alkoxide. And then what I can do is react that material with an alkyl halide. So let's say we use propyl bromide. Now I have a strongly negative oxygen and a primary alkyl halide. I can do SN2 substitution here. And so that would allow me to tack on that 3-carbon piece to the oxygen. So that use of an alkoxide, an O- with an alkyl halide to do an SN2 reaction, that's known as the Williamson ether synthesis. So this is a really common way to make ethers. Really all you have to do here is pay attention to SN2 rules, right? We can really only do this in ways that promote SN2 chemistry, right? So if we can't do this with very bulky groups, we can't do this with aromatic groups. So I could ask a question, for instance, like this. What would be the route to make this ether by Williamson ether synthesis? So in principle, I could think about cleaving this on either side of the oxygen, but practically speaking, I have to worry about breaking it up here into these two components, where I will use the alkoxide of phenol plus some alkyl halide at this position, because this is a place that's compatible with SN2, right? This is a primary alkyl halide, whereas if I were to switch it to the other side, I can't do a substitution at that benzene ring because it's sp2 hybridized. So if I wanted to outline a synthesis of this material, I would need to start with phenol, remove its proton with sodium hydride, and then add in, for instance, this alkyl bromide to carry out that synthesis. But this is a really versatile and useful way to make ethers because there are lots of different alcohols that we can buy, and there are lots of different alkyl halides that can do SN2 chemistry, so we can use this strategy a lot to make ethers. Okay? So those are the two ways that we've learned to synthesize ethers in Sophomore Organic 1, and that's really all we need to worry about for this class. So what we're going to talk about next is going to be synthesis of epoxides. Okay, and those we have two routes to do here. This is another series of events that we've already learned in Organic 1, but the first one is a peroxy acid oxidation. And so what this reaction looks like, and this is one you've probably seen before, this reaction takes a carbon-carbon double bond, like cyclohexene, reacts it with a peroxy acid, which has this general structure. So it looks like a carboxylic acid, but it's got this extra oxygen in there. And what that reaction will do is give us oxidation of that double bond to an epoxide. Okay? And the most common peroxy acid reagent that we will use is one known as MCPBA. And that stands for metachloroparabenzoic acid. So again, that is abbreviated MCPBA. It has this structure. So you'll see that it has that important part, which is that peroxy acid functional group. But this particular compound is less reactive and less prone to explosion than other peroxy acids. So this is the one that people will typically generate. So the mechanism here that we need to worry about of how this works, it's actually known as the butterfly mechanism. For reasons that I don't particularly understand, because it doesn't really look like a butterfly at all, but that's what we call it. So I'm going to draw that peroxy acid in kind of a folded up manner. And what we'll be able to do is have that interact with a carbon-carbon double bond in this way. This reaction happens where all the bonds form and break at the same time. So this is what we call a concerted reaction. But the way it starts is the pi bond of the alkene will come up and grab that oxygen on the far end. That makes this weak oxygen-oxygen bond break, and the electrons in that bond will fold over to make a new carbonyl, which causes the existing carbonyl to break and grab this proton, which then frees up this remaining pair of electrons to come back down to form that epoxide. And so that gives me straight away access to this epoxide here. So let's talk through that one more time. All this happens at the same time. What ends up happening, again, the pi bond will reach out and grab that oxygen on the end, breaking the oxygen-oxygen bond, which folds over to form a new carbonyl that breaks the existing carbonyl in the peracid to grab a proton, which frees up this pair of electrons in the OH bond to sit down and form the second bond of the epoxide. And so what we get out of this is the epoxide plus the reduced acid, right? If we oxidize the alkene, we have to reduce the peracid to a carboxylic acid. So we get that as a stoichiometric byproduct. A couple things about this reaction. Since it's concerted, that means that it's what we call stereospecific. And so what I mean by stereospecific is that if I have a substrate like these two alkenes where the stereochemistry is set in the alkene substrate, so if I have a trans alkene or a cis alkene, if I react that with MCPBA, what I will get is retention of that stereochemistry in the product. So a trans double bond is going to give straight away to a trans epoxide. If I do an MCPBA reaction with a cis alkene, the product epoxide will also be cis. So that's what I mean by stereospecific. The stereochemistry of the starting material is directly reflected in the product. Okay, so that's one very common way that we can use to make epoxides in this class. So we can do just a few examples here. So with this one, if I treat it with MCPBA, so what that means is I'll just put that, I'll set that oxygen down on the carbons that used to be involved in the double bond, go directly from the alkene to the epoxide. In a case like the second example where I have a Z-configured alkene, I will get the product epoxide will also have those two ethyl groups on the same side of that epoxide because they're on the same side of the carbon-carbon double bond. So I do see that stereochemistry reflected in the product. Okay, so that's the first way, and by far and away the most common way that we synthesize epoxides. The second way that we need to worry about for synthesizing epoxides is what we will call a ring closure of halohydrons. So this is also kind of harkens back to sophomore organic 1. This is a reaction that you probably remember. If I take a carbon-carbon double bond and I treat it with a halogenating agent like bromine, but in the presence of a nucleophilic solvent like water, you may recall that I will make that bromonium ion, and that undergoes ring opening by the water. Okay, and so then after we lose that proton off of water, we get a halohydron product, which looks like this, where the bromine is on the less substituted carbon and the OH is on the most. That's what we call a halohydron. Right, and so that's a reaction from sophomore organic chemistry 1. If we can do that and then follow that reaction up with a ring closure step where we will treat that halohydron with sodium hydride, sodium hydride will allow us to remove the proton from that alcohol of the halohydrin, and that gives me a good nucleophile which can ring close and spit out the bromine through an SN2 reaction, and that actually takes me to an epoxide product. So this is another way in which we can make epoxides, where we will ring close a halohydrin from a normal alkene reaction to make an epoxide. Now, this is not a very common way that people use to make epoxides now, but it is one that you see frequently in the historical literature. So let's look at just a couple of examples there. So let's look at this 5-membered ring double bond. So if I do this reaction, Br2 with H2O, in the first step, I will get a halohydrin product, again, where the OH will end up on the most substituted carbon, and the bromine will end up on the least. And that arrangement of OH versus bromine is always going to be anti with respect to the ring, again, because they have to happen from the nucleophile adds from the opposite face of the bromonium ion. So I would get this plus its enantiomer. And then if I treat this material with sodium hydride, pluck off that hydrogen, it will ring close to an epoxide to give me this epoxide plus its enantiomer. So if we want to look at one more example of something like this, we can treat this double bond, Br2 in water. In the second step, sodium hydride. Again, that first step's going to give me this material, halohydrin formation. Second step, we'll close that to the epoxide. Okay, so those are the routes that we can take to synthesize ethers and to synthesize epoxides. The next video that I will upload and send to you will talk about reactions of epoxides and ethers. As I said already, the ethers are pretty unreactive, so we really only have one reaction to worry about for those. And then the epoxides, we'll see some strategies where we can ring open epoxides under a variety of different conditions.